All right, 12.2, fundamentals, or fundamental, counting, principal, and factorials. So we're going to be doing some of the similar things here. We'll talk about the first ones in a minute here, but if I look at 10, 11, one's on the back side here, different types of arrangements, but if I just read, say, question 11, shall participate in exactly one sport, one club, one committee, 5 sports, 7 clubs, 4 committees. Could we build a tree diagram of this? Sure. Yeah, we could build a tree diagram of that. But would we want to?
No.
Because it's going to be over 100 different outcomes going on here. And Sam, if you're watching, no vocab. No vocab. Here we go. So we're in notes here. No vocab. But we're going to look at a better way than tree diagrams. Again, we talked about tree diagrams have their time and place. They are excellent at showing visual representations of all the different outcomes. They're awesome to show you how many total outcomes there are. But if you start getting like more than 50 different outcomes that are available, well, building a tree diagram to show all that would just spend a lot of time. And that's the problem with the tree diagram here. So we're going to be looking at some different ways here. So where it starts here, if you look at 1 through 9 here, these are math problems. They make some interesting memes sometimes, factorial with the symbol there. So I'm just looking at number 3. And what it says is this. And this symbol here is the symbol for a factorial. And what exactly is a factorial? So what this represents here, when you see this symbol, this 9 with that X, it's basically an exclamation point, right? But what that means is this. Instead of writing all this out, it means 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2, all the way down to times 1. And regardless of what the symbol is here, it always ends in times 1. So if I had, for example, 5 factorial, well, that's basically just 5 times 4 times 3 times 2 times 1. Okay? A 0 factorial, for what it's worth, is just the number 1. It's not 0. Okay? So officially, a 1 factorial is 1 times 1, but they both are kind of the same thing. But if you see this 0 factorial, and I only mention it because you see number 6, we see it right there, that's not 0. It equals 1. And then the 1 factorial is 1 times 1, which also equals 1. So 2 factorial then would be 2 times 1, and 3 factorial, 3 times 2 times 1, and so forth. So if I go to the 5 factorial, we'll just start with that. I could certainly go, if I see this here, and said, well, what does that equal? And I can go, oh, okay, I can go 5 times 4 times 3 times 2, and then if you really want to do times 1, I guess you could, but I could go, it equals 120. Do you agree with that? 5 times 4 times 3 times 2 times 1, boom. So you could certainly punch them in that way, but your calculators have this button right on it. And to get it, if I wanted to calculate it, this is what you do. You push the 5, and then what you need to do is you need to push this green second button up here, right? So I push that. And then the 3 right here, it's hard to see. I'll put it real close, but that X, you can see there's the explanation point there.
Oh,
So I push that, and then boom, there's my 120.
that's fun.
So if I had 6 factorial, I could do 6 times 5, on a calculator Jackson has. I could certainly figure it out, 6 times 5 times 4 times 3. Or I could just push 6, push that second button, and then push the 3. And I can see that 6 factorial is just equal to 720. So you can do it either way, whatever is easier for you. Obviously, it's faster just to use the factorial button, and I would use it instead of punching these things all in one at a time, but it's kind of your choice. So number 3 says 9 factorial. I suppose on your own. Go ahead, figure out what 9 factorial is.
Whoa.
Eve, what did you come up with?
362,880.
Right. That's exactly what it is. And this, of course, is it broken all the way out. Did you use the factorial button? Eve's keeping that info to herself.
She just doesn't want to tell us.
Did you use the factorial button?
Yes.
Yeah. So anyway, that's just how you access that information. We'll use factorials a bit here. So let's look at number 5. So when you're doing these here, okay, you need to figure out the factorials first. So what's 5 factorial? It's 120. What's 2 factorial? 2. And what's 120 minus 2?
182.
That's my answer right there. What you don't want to do is go, oh, 5 minus 2 is 3, and 3 factorial is 6. The answer is not 6. That is what 3 factorial is, but you have to turn these into numbers first before you subtract. Don't just go, oh, 5 minus 2 is 3, and 3 factorial, 3 times 2 times 1 is 6. The answer is 6. That's not how this works. So you basically, and you'll see some different orders of operation, but same kind of deal going on here. So try number 7. And I can show you a different way you can write these out too, but 6 factorial divided by 3 factorial. Pull a stick here and you can tell me what the answer is.
Hang on a minute.
Okay. Faith, what do you think?
120.
120?
Yep. 20.
120 is correct here. So, and again, you can think about this. I could figure out 6 factorial, which is 720, divided by 3 factorial is 6, and then 720 divided by 6 is 120. But if I wrote it out all the way here, you can kind of see it in a different way here. And later on this chapter, this will have some value for us here. But this is me just writing it all the way out, but then I can simplify stuff.
For number 6, for the 0, the exclamation point one, would you just add it to 6 and then do the?
You'd figure out what 6 factorial is. Jackson, you're probably good to go. I see it's after 1 o'clock, but quiz go okay?
Yeah.
Okay, we'll try and find a time tomorrow to check the next 3 here, but this is good. We moved it ahead, so
Yeah.
I'm happy about this.
Yep.
Try and figure out what Sig is up to for me, if you could.
Like,
And Sig the pig to finish it up there.
oh, he's still out
I
there?
think so. You give him a kick in the arse. So anyway, here you could see that these would cancel out, these would cancel out, and these would cancel out. And what do you think 6 times 5 times
He has
4
one
is?
more problem.
Okay. Well, so under 20 minutes, you think, for him? Oh, there he is. The man, the legend has returned here. Okay, thanks, Sig. Good to go. You're all good. Have a good one. Not a great one, just a good one. Not a great one. Doesn't need to be great, so. Yeah, but this is kind of how it is. And again, we're going to do, when we get to permutations and combinations, stuff like this is going to be coming into play again. And you can, so just seeing how this looks here has benefit, but one and the same. You most likely solved it this way, but you certainly could have just solved it this way and realized these things cross out. both ways, 720 divided by 6 or 6 times 5 times 4. Both of them get us to the correct answer. And yeah, for number 6, again, you'll figure out what 6 factorial is. And then you'll add 0 factorial, basically 6 factorial plus 1 is your final answer for that one there. So, try number 9, I suppose. Again, a couple things going on, but same thing. Try and turn those into real numbers.
Those are fake numbers.
Right. You're solving it. I'm going to write it out the long way.
You want us to write out the long way?
No, you guys can just solve, but I'm just going to show you how it works and how it could look here.
I wonder who it's gonna be.
Yeah, I know.
I have
Big
no
mystery
idea.
here.
There's so many people left.
Colin, what do you think?
180?
180? 180 is correct. So, yep, it is 180. But again, this is how it would look. Basically, it's the same as 6 times 5 times 3 times 2 times 1, because there's my 6 factorial multiplied by my 3 factorial divided by my 4 factorial. And you can see again how everything crosses off, and all I'm really left with is the 6, the 5, the 3, the 2, and the 1 multiplied together there on the top. Yes?
Yep.
Okay, good. So let's talk about the next part, fundamental counting principle here.
This is scary.
Huh?
This is scary.
Well, not so much here. I'll give you a couple ways to think about it here. So, well, let's talk about number 11 here. So, here it is. It says, we read it before, but 1 sport, 1 club, 1 committee. 5 sports, 7 clubs, 4 committees. How many different choices of the 3 activities are there? Or how many total outcomes are there? If I would build a tree diagram, you could say. So the counting principle, how it works here, the way they write it out is more confusing than anything here, but that's why I don't want to define this here. But what we do is we take how many possible outcomes for every event there are. So it says 1 sport. So how many different sports are there to choose from?
5.
And she could pick any of the 5, whatever they may be, right? Golf, football, whatever. But there are 5 different sports to choose from. 1 club. How many clubs are there to choose from? 7. And how many committees are there to choose from? 4.
And then you just do that?
So what's 5 times 7 times 4?
140.
That's how many different outcomes there are. Outcomes or choices or whatever you want here. And again, I'll show it to you another way, a simpler way, back to tree diagrams. Let's just say flip a coin. That's the answer. There's 140 choices. Let's go back to something simpler, such as yesterday. Let's just say flip a coin, roll a die. How many different outcomes are there if I flip a coin and roll a die? Yeah, I got heads or tails, and then a 1, a 2, a 3, a 4, a 5, or a 6. And where I get the tails, and same deal. The 1, the 4, the 5, the 6. Count it up. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 12 outcomes here. Agreed? Yes. But if I use fundamental counting principle, if I flip a coin, how many outcomes are there? 2. I could get the heads, I could get the tails. There's 2 total outcomes. If I roll a die, how many outcomes are there? 6. I could get the 1, the 2, the 3, the 4, the 5, or the 6. And if I multiply the number of outcomes at each of those events, 2 times 6 is 12. Same information is provided. tree diagram, fundamental counting principle, but one of them is more visual. I mean, you can see all the different outcomes here. This one, we just know how many outcomes there are. And I think tomorrow's lesson, 12.3, theoretical probability, is all about most probability lessons. You need to know how many total outcomes there are. It's the number of favorable outcomes over the number of total outcomes. So fundamental counting principle, tree diagrams, they both will show you how many total outcomes there are. That is a key number we're going to need the rest of this chapter here. So we know for any probability that we're going to do, again, we need two things, but this is one of the numbers we must have. We must know how many total outcomes there are. I'll give you another scenario here. I'm going to say you're building a sandwich and you got 4 choices of bread, 9 choices of cheese, right, 16 choices of meat,
Goodness.
and 2 choices of vegetables.
I think you just might be hungry.
I think
So-
you're hungry.
How many different sandwich combinations could I create? You guys already know it, all right.
1,152 combinations.
4 times 9 times 16 times 2. Did you say that number to me?
Yeah.
There you go.
That's a lot of combinations.
That is.
That's a
That's how
lot.
many different sandwiches I could get: the white bread with the cheddar
I-
cheese, the roast beef, and the lettuce.
You have to make it your mission to make every
And then
combination.
1,151 more different ways I
I
could
think we
build,
should spend an
build a
entire
sandwich.
class
So
or an entire day just trying to make 1,152 sandwich combinations.
that would be
Like, you should see if you can get us like the entire day.
time so horribly spent. So
No.
Well, then we could give them to homeless people. Here, take this sandwich. Take like 16 of these sandwiches. We don't need this
All right.
many.
We have a
So let's look on the back side here. So this is a little different here in the way the number of things can be grouped here. And again, we're going to expand upon this a little bit more here once we get to permutations and combinations later on this chapter. So 13 says, determine how many 2-digit numbers can be formed with the digits 1, 3, and 5 if digits cannot be repeated. So when you're solving this type of problem, again, how many 2-digit numbers, 2-digit numbers can be formed with the digits 1, 3, and 5 if the digits cannot be repeated. So in this case here, for the first number, how many different choices do I have for what the first number could be?
3.
I got 3 because it could be a 1, it could be a 3, or it could be a 5. It could be any of those here, right? There are 3 choices. And then for the second number, how many choices do I have?
3.
Five.
Well, there's only 3 numbers.
1, 2,
5.
6.
Well, think of it. It says it's a 2-digit number, right? And then the first number, let's just make up a number. Let's just say the first digit's a 1. Okay? So the second digit, what could it be? A 3 or a 5. So how many choices do I have for that second digit? I got 2. Because I'm not repeating. I can't repeat the digit. So I only got two choices of what it could be. Because if the first digit's a 1, well then the second digit can't be a 1. It could be a 3 or a 5. If the first digit's a 5, well the second digit can be a 1 or a 3, but it can't be a 5 because I'm not repeating, right? So how many different 2-digit number combinations can I make? 3 times 2, that's it. And I could list them all out here. I could do 13, 15, 31, 35, 51, or 53. There they are. Find me a different 2-digit number using 1, 3, and 5 where the digits don't repeat. You checking, Colin? Looking for a 2-digit number using 1, 3, and 5 where the 2 digits don't repeat?
Me?
Colin is considering.
Oh, you gave us a problem?
No, I'm just showing you here, like, these are your 6 options. I wrote them all out here. It doesn't take long to think of. There's only 6 outcomes, but again, you can think about it here. If the first number is a 1, again, I got 1, 2, 3 numbers, what the first number could be. But whatever it is, say it's a 1, well, the second digit, now I only have 2 choices here. What if I said, same question, how many 3-digit numbers could be formed with the digits 1, 3, and 5 if the digits can't be repeated?
Can you pick whatever first number you want?
No, 1, 3, or 5. Well, you can, but you can only use the numbers provided here,
Oh, okay.
and you can't repeat them. So if I said a 3-digit number, can't repeat the digits, 1, 3, or 5, how many different number combinations? You say 3?
I say 3.
6? So I can take the same thing here, but then how many choices would I have for the third number? I would only have 1 number left.
Oh, good, it would be 6.
Because if I'm using 1, 3, or 5, and I use the 1 and the 3, what's the only number that could possibly be my third digit? 5. And here it would have to be a 3, here would be a 5, here it would be a 1, here it would be a 3, and here it would be a 1.
I
There
don't
they
know.
are. It's 3 times 2 times 1 this time. So a 2-digit thing is 3 times 2. First digit, 3 choices. Second digit, 2 choices. A 3-digit number, still 3 choices for the first number, 2 choices for the second number, but the last number, I would only have 1 digit left.
Yeah.
So in this case, they'd both be the same, just because the difference would be this for a 3-digit number, and of course, multiplying anything by 1 doesn't change the value of anything. But there they would be, 3-digit numbers. So try number 15 on your own. It says, find the number of ways that 11 children can be arranged in one row of 11 chairs. And again, you figure, pick a kid, throw it in a chair, or gently have them sit in a chair on
throw
their
it.
own. Might be a better way to phrase that.
Throw it.
Ask the kid kindly to please have a seat.
No.
But then, when you get to the second chair, how many people do you have left to choose from? Because again, the first kid's in a chair, right? And then the third chair, how many do you have left? The fourth chair, how many do you have left? And so on and so forth there. So, how many different ways could I arrange 11 kids that are going to sit in one row of 11 chairs?
I don't know how to say this number. Can I see the number?
Sure.
Can I say it? Wait, no, I want it.
What is it?
Okay, here we go. 39,916,800.
Right. But think about what we did. Like, again, first kid, 11 choices. Second kid, 10 choices. Third kid, 9 choices. Fourth kid, 8. All the way down till when we get to the 11th kid, there's only 1 kid left.
You could just take the amount of things. and
So
then
really-
do the-
Really, when you thought it through here, this was actually just this. 11, second, 3, boom.
That's what I did.
Right, that's exactly what this was a factorial here. Because you're going all the way down to times 1. The factorial button will always take you down to times 1. And that's kind of what these word problems are. You're going to use your factorial button here, or you could. So I think this one they probably meant to write a 3-digit number here, to be honest with you, because everything else is down to the end here. But let me ask you this here. Similar question. I'm going to say, because you'll see these types of questions here in your homework and all that. So now I'm going to say 5 digits. 1, 3, 5, 7, and 9. Okay? How many 5-digit numbers can I make if I don't repeat the values?
Do you just need to type all of that out?
Huh?
Do you just need to type it all out?
You can. I mean, however you want to do it, but think about it. You're multiplying.
Oh, wait.
your first digit, how many choices do you have? Your second digit, how many choices do you have? Your third digit, how many choices?
120.
Yeah, because your first digit, I'd have 5 choices. And then the second digit, I'd have 4 choices, right? Because I can't repeat whatever number. And then I'd only have 3 choices and then 2. And then the last digit would have to be whatever of the 5 digits I actually have left. That's the only one it could possibly be. So I would have 120 different things. Now, let me ask you this. Same thing, 13579, 5-digit number. If numbers can be repeated.
Good question.
Now, how many choices do I have here? So I'm saying like 1, 1, 1, 1, 1. Could be 1. So
Could you double?
So let me ask you this. The first digit, and I'm saying you can repeat as many numbers as you want here. Okay? So the first digit, not 240,
120.
not 120.
Wait,
That's
let me cook.
I'll give Faith a minute here, see what she comes up with here.
Is she doing it?
And then we'll work it out
Colin, how
here.
you go over there?
3,125.
Yes, that's the correct
How
answer.
did you get that?
So think
How did you
it,
get that?
5
well-
times 5 times 5 times 5.
Oh,
but think about it. The first digit, how many choices of numbers do I have?
5.
I got 5. The second digit, how many choices of numbers do I have?
oh my gosh.
5, because I can repeat the numbers. The third digit, how many choices do I have? 5.
Oh, no.
And then the fourth digit,
5.
and then finally the last digit.
5,
5.
4.
Right, and that's how this one could work. So if I don't repeat or repeat, it changes how many different outcomes I have at each step. Because if I can't repeat and I can't use that number again, well then I have fewer options each step of the way. But if I can keep using the same numbers over and over and over, well, I have 5 digits. That could be, because I could have 11111 as a number. I just use the number 1 all 5 times. Or I could have 13513. I mean, it doesn't really matter. But all 5 numbers. So you see kind of how that changed with those two? Like, if I don't repeat and if I do repeat, you just consider, well, how many choices do I have first? How many choices do I have second, third, and however long you got to go through the process here, right? Try number 17. Last one here, I think. So, you are on a school field trip and want to take a class photo with the students standing in a row. There are 10 students that will be in the photo. The class president will stand way to the right. The vice president will stand way to the left. In how many ways can you arrange the remaining
Okay, so
students?
just
I know
subtract
I
2.
know it. I'm gonna do it.
Mhm.
I did it.
Yep, you're right, Colin.
I did it.
Was that-
Because how many people are we actually arranging?
And then you factorial that, right?
Good, because we're going all the way down. We're using
Oh.
every single one of them here. So what is it, Colin?
40,320.
Right.
That's a lot of
Because
ways.
you're only positioning the president
And the vice president.
and the vice president.
They're already locked, so we're
So
not
you're
counting
only-
them per
you're
se.
only,
It's
moving around.
it's the right. So it's
Yeah.
8 times 7 times
Yeah.
6 times 5 times 4 times 3 times 2 times 1. That's what it is. And that's the whole key here, that you don't use 10 because 2 of them they're not being positioned. We're not considering them because you're standing here, you're standing here, but the remaining 8, we don't really care. How you guys go
Go
to just
wherever.
get however you want type of deal here. And then again, that's the whole thing. Just not a crushingly difficult problem, but again, I think you probably saw it too. And just understanding, wait a second here, it's not 10 factorial because 2 of them they're locked in place.
They're locked.
They have no options of where they're going to
I
go.
wanna go in the middle.
They're there. Well, that's one of the 40,000
No, I mean, if I
possible
was the vice
combinations.
president,
Are we
what
not-
if you said you wanna be in the middle?
Well, that's not how these people want to do it on the school field trip, so, you know, it's a school field trip, Colin, that changes everything.
Yeah, you have to look good for your field trip.
But I don't wanna be on the side, I wanna be in the middle.
Would you
Okay.
rather be in a monkey exhibit? Put you in the back.
So,
in a monkey
be careful with 18, I mean, it's not,
class.
again, a little longer, but just so to help you here. 4 flavors of ice cream, 3 different toppings, 2 sprinkles. You are allowed to pick 2 scoops of ice cream, which can be the same flavor.
Yeah.
2 scoops. They could be the same flavor, which means I could repeat. I could have chocolate.
Well, multiply by
Repeat
2,
it four times.
am I right?
Not 4 times, 2 scoops.
Multiply by 2.
Well, how many choices do I have for the first scoop of ice cream?
So do 4 times
4.
4.
Right, because the
Well,
first scoop
16.
of ice cream, I got 4 choices. The second scoop of ice cream,
And
I
then
got 4
multiply by
choices.
3 and 2.
Right, and then 1 type of sprinkles, 1 topping. But that's the whole key now. You know. So not terribly hard to do. It's just, again, you got to read the question and just kind of think about, wait a second here. How many things are going on? There are 4. Scoop 1, scoop 2, topping, and sprinkles. So I'd be multiplying 4 things together.
That's
And
how
then
we
you
do
got to
ice
think,
cream.
well, the ice cream here, oh, and this is the key thing here, the ice cream, which can be the same flavor. So then this is similar to like this thing here where I could repeat. I could have double, you know, give me 2 scoops of chocolate. Hold the peanut butter though. Right.
Are we done?
2 scoops of chocolate, hold the vanilla.
No, give me the vanilla, I don't like chocolate ice cream.
I love
Like and
chocolate.
subscribe.
Bye.
There we go.